Okay, do you have any questions? If you remember the last week, we had ended the lecture with a short discussion on electric field lines. We will pick up from there. We will define what is an electric field, how we define the electric field lines, and then study some sample systems and calculate the electric fields in various simple cases. But do you have any questions before? Now, there's just one change of notation I will be discussing before we start. You see, we had written the force before as K times Q1 times Q2 divided by R squared multiplied by R12 hat, where we were imagining this is Q1. We had the second charge Q2. R12 hat is along this line pointing from the charge. Well, that was basically how I defined this. This is R12 hat. So this is the force acting on the charge 2 due to the charge 1. So if you write the force in this form, we said that, okay, everything, whether the charges are the same sign or the opposite sign, this is always true. And this constant K is usually written as 1 over 4 pi epsilon 0. It is just a definition. Now, we will see later on why we write it in this way, because although this Coulomb's law, the force law, becomes somewhat more complicated in this form, 1 over 4 pi epsilon 0, Q1, Q2 over R squared times R12 hat. Some other laws that we will see later on will have a simpler form in terms of this epsilon 0. And I just want to mention that this is equal to 1 over epsilon 0 Q1, Q2 over 4 pi R squared. Just pay attention to that factor. Now, we will come to that factor later on. If you notice, that is just the surface area of a sphere of radius r in 3 dimensions. Now, then we said that, okay, the force created by a charge, in fact, if you have many charges around, eventually we will have infinitely many charges. Let's just call them Q1, Q2, Q3, Qn, etc. We just give them some names, and now we put another charge somewhere else, Q. Then we said that there is the superposition principle, which says that if at this point Q, Q1 exerts a force F1 in this direction, if Q2 exerts a force, let's say F2 in this direction, etc., then the total force acting on the charge Q is just vectorial sum of all these vectors. All the forces created by each one of the capital Q's separately. It's just the sum. This, we said, is called the superposition. But also note that this, let's just sum over I. This is 1 over 4 pi epsilon 0. The force created by, let's say, this charge over here will be 1 over 4 pi epsilon 0 times the Q times the charge of the other charge creating the force divided by their separation squared. Let me just use this notation. Well, what each one of these symbols means, okay, I am looking at this charge Qi over there, an arbitrary one. It will create a force in this direction. Let me just call it Fi. So this will be the direction. I don't really know whether it is positive or negative. I'm just choosing some arbitrary direction for the purpose of the sketch. And then I need to write the force created by this charge, which is, the Coulomb's law tells me that it is 1 over 4 pi epsilon 0. The product of the charges that is feeling the force and the charge that is creating the force is just Q times Qi, divided by their separation squared. This distance I call Ri. And then it is in the direction, in its direction, the force is in the direction which is along this line. Well, this Ri vector, by definition, is pointing away from the charges. So this is my Ri hat vector. Of course, if the charges have opposite sign, the force Fi will be pointing in that direction, in the opposite direction, but that is already taken care of in this expression. Because if the charges are opposite, they have the opposite sign, the product is negative. So a negative number multiplied by a vector just points in the opposite direction. So it's already taken care of. So is this expression clear to you, or do you want me to repeat? Okay, quite often, sometimes students come to me and say that, oh, I didn't ask it in the class because I thought my friends were understanding. And then it turns out that 80% of the students couldn't follow. So if it's not clear, just ask me. Yes? Yeah. Okay, sorry for my handwriting. This is for 4 pi epsilon 0. This is 4, this is pi, this is a hat. Now, once some students ask me, why do I put n's at the top of some symbols? Do I take the nth power? That's a hat. Yes, this is a unit vector. The hat just shows that it's a unit vector. So since we are dealing with forces which have just the magnitude and the direction, I have to somehow show the direction. And this vector shows me the direction. Now, for me, what will be important here is, you see, all these terms in the sum, they are proportional to Q. So I can just take it out of that summation sign. Well, the rest I will leave inside the summation. Now, what this tells me is that the electric force that a charge feels, remember, I'm writing the force that this charge over here is feeling. This is the force that this charge feels. And the force it feels is always proportional to its charge, multiplied by some other quantity, which is determined by the other charges. So this thing in parentheses is determined completely by all these charges over here. If I know their position, if I pick this point, I can calculate whatever this is. So if I can calculate this quantity, then if I put some charge over here, I know what the force it will feel, because it will be just the charge multiplied by this quantity. And that quantity is what we call the electric field. This is the electric field created by the charges capital Qi. So one thing is, well, at least if you write it in this form, it automatically satisfies the superposition principle. So if one charge is creating one electric field at a given point, the other charge is creating another electric field at the same point, the total electric field will be just the sum of the electric fields. So let's see what it depends on, the electric field created at a given point. You see, one thing is clear, it depends on these charges. So that I have these charges that is creating the electric field. It also depends on at which point I'm evaluating the electric field. You see, here, instead of this point, if I choose some different point, okay, the QIs will be the same, assuming they are fixed. These will be the same, but all these distances and these directions, they will be different for a point over here. So if I change my point, the electric field will be different. If I change the configuration of my charges, again, the electric field will be different. So it depends on both the charges creating the electric field and at which point I am evaluating it. So in general, when we are talking about the electric field, we talk about the electric field at a point P. This is sum over I, 1 over 4 pi epsilon 0. This sum over I just basically means that if you have many charges in your system, just calculate the electric field created by your charges. So each one of this terms, this term is the electric field created by the charge Qi, one of them. I'm just summing over all of them to calculate the total electric field at the point P. So let's do an example. Let's assume I have one charge over here, Q. Another charge over here, minus Q. Let me just also write this one. So if you put a charge Q at a given point, the force it will feel will be its charge multiplied by the electric field at its position, at the position of the charge. Now let's come to this example. Okay, let us try to calculate the electric field somewhere along this line, in the middle. So let's say this is d over 2, this distance is d over 2. And I want to calculate the electric field at this point, let's say P. Well, I have two charges. I have to calculate the electric fields that each one of them creates first. So let me start with the plus Q charge. So let me imagine this straight line. So the electric field created over here will be pointing away from the positive charge. So it will be in this direction. Let me call that E1. Now the electric field always points away from the positive charge. Why? Well, you see, this vector is always pointing away from Qi. That was how we defined it. You see, if you go back, this was the charge Qi. At this point, this unit vector is pointing away. And that unit vector is multiplied by the charge itself. So if charge is positive, we multiply a unit vector with some positive quantity. So the result is, again, pointing away in the same direction. If charge is negative, then we are multiplying a vector, which is pointing away, by a negative quantity. If you multiply a vector with a negative quantity, you obtain a vector pointing in the opposite direction. So that's why the electric field always points away from the positive charges and towards the negative charges. So that's what I used over here. Here I have a positive charge. It's creating an electric field at this point, and it will be pointing away. Then I have a negative charge over here. It will also be creating an electric field at that point P. But this time, since it's a negative charge, the electric field will be pointing towards the negative charge. So this is my, let me call it E2. Now let's call this R. Well, this distance will also be R, because I'm just basically looking at the point which is straight at the top of the midpoint. So the distance of this point from this charge and its distance from this charge will be the same. But you see, the magnitude of the electric field created by a charge is this constant 4 pi epsilon 0 multiplied by the charge creating the electric field. Well, the magnitude of both charges is just q, divided by the distance squared. Well, the distance is r for both cases. So this is the magnitude of the E1 electric field and also the magnitude of the E2 electric field. They both have the same magnitude. Well, let me imagine this horizon. Is this point clear? You see, the distance of this point from both charges are the same. So that is why both of them, and the charges have the same charge except on the sign. Their magnitudes are the same. So the electric fields they create will have the same magnitude. Now, if I imagine this horizontal line, horizontal meaning parallel to this one, well, you see, this angle over here is the same as this angle. Well, these two lines are parallel. This is the same as this angle over here, and this angle over here is the same as this angle over here. Again, I have two horizontal lines intersected by a third line. So this angle and this angle, they should be the same. But here, I have an equilateral triangle. This angle and this angle, they are also the same. Now, I have these two vectors. To sum them, well, I have to add them vectorially. I can geometrically add them. Take one of them. And move it to the end of the other one. Oops, sorry. I just move it here. So this will be my vector. This is E2 vector. So it will be just lying on this line. This is the total electric field. So the total electric field will be horizontal. Well, another way to see that, let me just copy that picture of the vector electric field vectors. This angle is theta, this angle is theta, they are the same. Let me just draw the vertical line also. Now, E1, let me just give them some names. Or the horizontal line, let me call x, the vertical line y. E1, I can just write as the magnitude of E1 times cosine theta in the I direction, plus E1 times sine theta in the j direction. If I just, this is the, you just imagine this right triangle This length is just E1 times cosine of this angle, the horizontal length. The vertical length is E1 times the sine of that angle. So this is my vector. Now, if we write E2, this triangle over here and this triangle over here are in fact identical. The only difference being it's just the mirror image of each other. So the lengths are basically the same. The horizontal length will be just E2 times cosine theta in the I direction. The vertical length is pointing downward in the minus y direction, minus j direction. So it's minus E2 sine theta j. Well, if you sum them, and keep in mind that these two are the same. You see here, we know that the magnitudes are the same. If we sum them, these will just cancel. The total electric field is twice E times cosine theta. Well, we know what E is. Twice E was 1 over 4 pi epsilon 0, Q over R squared. This is E. We need to calculate what cosine theta is, but you see, theta is this angle over here. This is my theta. And cosine theta is just d over 2 divided by r. Well, let me just cancel the 2's. Of course, in the I direction. So the total electric field is 1 over 4 pi epsilon 0, Q over R cubed, QD over R cubed in the I direction. So this is the electric field. So if we repeat what we did, okay, first we made the sketch, identify the electric field vectors created by various charges. Then we sum them vectorially. So it was easier for me to write first the components of the vectors and then sum the components to obtain the total electric field. And then I just simplified by just replacing some of the unknowns in terms of the other quantities given in the problem, like cosine theta. I could just read from this right triangle over here. This is the angle. The adjacent side is d over 2. The hypotenuse is r. So the cosine of that angle is d over 2 times r. Or if you like, you can, yeah, okay, that should be enough for now. Well, we can check various limits in this case, whether our result makes sense. You see, D is something we choose. I can change the separation of my charges. What happens if I set D equal to 0? What would you expect? Okay, you want a vertical electric field. That's what you expect. Okay. For example, that expectation doesn't hold. Because here, you see, whatever the value of D is, whatever the length, the R is, as long as we are along the line passing through the center, this vertical line, it is always horizontal. So that expectation doesn't hold. Why not? Okay, there are two things. Why did you expect it to be vertical if if two charges are at the same point? Either your expectation was wrong or this result is wrong. So we have to correct one of them. So why did you expect it to be vertical if I bring these two charges at the same point, to the same point. Okay. But what will be the charge of that point? 0. There won't be any charge. So if D is equal to 0, we don't expect any electric field. Well, does that hold? Yeah. You see, if D is 0, Q times D is 0, R is non-zero. Remember, R also depends on D. So at least one expectation holds. If D is equal to 0, we don't have any electric field. Now, this combination will be important later on, the charge times the separation. Now, any questions on this example? Because now we will be going on more complicated examples. So let's calculate the electric field of a very long wire. So this is my wire. And I want the electric field at this point. Now, if it's infinitely long, it cannot have a finite charge. I will just assume that let's just take some length. If this is L of a very long, uniformly charged, if I take a length L, I will assume that it has a charge Q. Since it is uniformly charged, the Q should be proportional to L. The longer a segment I take, the larger charge it will have. And Q should be proportional to L, and we call that proportionality constant lambda times L. Lambda is the linear charge density. It's the charge per unit length. Okay, now back to our problem. We have this infinite wire. It is definitely not a point charge. It's the Coulomb's law holds for point charges. We had already seen one example. You see here, although we derive this from Coulomb's law, we cannot just write it down from Coulomb's law. This doesn't look like Coulomb's law because this system is not a point charge. We have two charges. And similarly here, we cannot just write down the result using Coulomb's law because one of the system is not a point charge. But we can just divide our system into very small pieces. I will just imagine my charge to be, my wire to be divided into very small pieces. Each having a thickness, let me call it dx. Eventually, I will assume that I will take the limit as dx goes to 0, and it will become a point charge. Now, the electric field created by this dx at this point will be, well, first of all, along that line. If it's very small, you see the charge that very small segment has will be just lambda, the charge density, multiplied by the length. This is the charge of this very small segment. So the electric field created will be very small. That's why let me also put this different d sign over there, dE. This will be equal to 1 over 4 pi epsilon 0 multiplied by the charge creating the electric field, which is just dq, divided by the distance of the charge from the point at which we are evaluating the electric field. So let me call that distance r, r squared, multiplied by the direction of the electric field. Well, let me just denote it by r hat. This is the electric field created by this very small segment. Of course, if we want to calculate the total electric field at this point P, I have to sum over all these segments. Which will be a sum of 1 over 4 pi epsilon 0 dq over r squared times r hat. Now let's see, I am summing over these segments. I am summing over these segments. Now, as I am going over these segments, let's see what is changing, what is constant. Okay. As I go from one segment to other segment, 1 over 4 pi epsilon 0, does it change? This is just a constant. dq, does it change? Well, I will be assuming that dx is the same for all of them. So dq doesn't change. Does r change? So this depends on which segment I'm looking at. Does this unit vector change? Well, that's also changing. Now, eventually we will take the limit as dx goes to 0. So I will have infinitely many terms in that summation, and then the electric field becomes the integral of 1 over 4 pi epsilon 0 lambda dx over r squared times r vector. So what are the ranges of x? How do you find the limits of x? Well, you see, what I did as I'm going from summation to integration is, if I want to just sum over these, I have to give them some name. I have to give them some name so that I can distinguish which segment I'm talking about, I'm summing over. The easiest name that I can give to these is their x-coordinate. So if I want to talk about the x-coordinate of my segment, I have to choose an origin. Well, the easiest origin that I can choose will be this one. This is my origin. You can choose your origin wherever you like. This is just, it will turn out to be simpler. If that is my origin, well, what is the x-coordinate of my first segment? It is at minus infinity. I start from minus infinity. And also keep in mind, in certain problems, it will be important. When I'm defining dq to be like this, I am defining dx to be positive. So as I'm summing over various terms, I am increasing the x value. That is why I start from minus x and I go to minus infinity to plus infinity. It doesn't make any difference in the summation. I can just start from summing these terms and go to these segments, or start from these segments or go to these segments in positive x. But when you convert it to integral, it will make a difference. But by definition, I'm saying that the x is positive, so I'm incrementing my x. That is why I start from the smaller value to the larger value. Well, but essentially, the physics is over. So we wrote it as an integral. We calculated the electric field. The rest is calculus. Now we will do the calculus also. How do we evaluate that integral? Well, first let's do one thing. First, let's write this r hat vector in terms of the x and y coordinates. It's not so easy to calculate the integrals of vectors which are changing, which depends on my integration variable. So I will rather convert this r hat vector to I hat and j hat, which do not depend on my integration variable. So I can just take it out of the integral. Well, this was my r hat. This is my r hat vector. Let me call this angle theta. So it has a horizontal component and a vertical component. Let's say this is x direction, this is the y direction. You see, as I change my segment, okay, r hat vector changes, but x direction and y direction, they are constant. They are independent of my integration variable. So this length over here is cosine theta. And this length is sine theta. So which basically tells me that this my r hat vector is just cosine theta in the x direction, plus in the I hat direction, plus sine theta in the j hat direction. This is equal to, from minus infinity to infinity, 1 over 4 pi epsilon 0, lambda times dx over r squared cosine theta in the I hat direction, plus from minus infinity to infinity, 1 over 4 pi epsilon 0, lambda dx over r squared sine theta in the j hat direction. Okay, now I have theta, r, and x. They are all related to each other. Let's find something else that is constant as I'm changing my segment. As I'm changing my segment, what else doesn't change? What doesn't change? What is r? Well, small r changes. This segment is further away than this segment. So as I'm going from this segment to this segment, this r changes. But this doesn't change. Let me call that capital R. So what I will do next is, well, you see here I have 3 parameters that are constantly changing, which all depend on each other. I will just pick one of them and express everything in terms of that parameter and the other constants in the problem, like r is a constant. So let's see. What is cosine theta? Or, so which parameter do you like? Do you like theta, x, or r? Theta. Okay, so let's express everything, all the other parameters in terms of theta. Now, on one hand, I have this x. This is my x. Now, what is tangent theta in that figure? R over x. R over minus x. Basically, because in that figure, I define theta to be this angle. The x-coordinate of this point is minus x. Sorry, the x-coordinate of this point is x, which is a negative number. But tangent of theta is r over the absolute value of this. So that's minus x. That's why I inserted a minus sign over there. Or x is equal to minus r over tangent theta. What is dx? Well, let's see, r over tangent squared theta times the derivative of tangent theta with respect to x, no, with respect to theta, no, or the differential of tangent theta, let's say. What is the differential of tangent theta? It is the theta over cosine squared theta. Or dx just becomes r over sine squared theta times d theta. Okay, one thing done, dx is done. Cosine theta and sine theta, they are already expressed in terms of theta. And we have to express r in terms of theta. Well, the easy thing is sine theta is capital R over small r, or small r is capital R over sine theta. Now let's put all together. The electric field at the point P. This is 1 over 4 pi epsilon 0. It's a constant. I took it out of the integration sign. I hat is just a constant. I took it out. Lambda is a constant. I took it out. So what is left inside is, instead of dx, I have r over sine squared theta, d theta. And then I have 1 over r squared. Well, r squared, I just calculated. You see, it's capital R over sine theta. So it's capital R squared over sine theta. Capital R squared over sine squared theta. And then I have the cosine theta. Well, nice. It's simplified. Sine squared theta, they just cancel. This cancels one of them. And then I have the other term. It's basically exactly the same term along the j direction. The only difference being, instead of cosine theta, I have sine theta. Again, these sine squares, they will cancel. R will cancel one of them. So what are the limits now? You see, we said that x starts from minus infinity. What is the value of theta when x is minus infinity? Well, this angle gets smaller and smaller and smaller. So when x is minus infinity, theta is 0. That is the lower limit. The upper limit, as x gets closer and closer, you see, we start from 0 degrees. As I am approaching this origin, theta becomes pi over 2. As I'm going towards plus infinity, theta becomes larger and larger and larger. Eventually, it's a line. So what is the angle theta? Pi, 180 degrees. So the limit is from 0 to pi. So the electric field at the point P is 1 over 4 pi epsilon 0, I times lambda times the integral from 0 to pi. I also have 1 over r. This is I hat. The theta, cosine theta, plus 1 over 4 pi epsilon 0 I j lambda over r from 0 to pi the theta sine theta. Let's evaluate the integrals. 1 over 4 pi epsilon 0 lambda over r in the I hat direction. The integral of cosine theta, sine theta, when theta goes from 0 to pi, plus 1 over 4 pi epsilon 0 lambda over r in the j direction, the integral of sine theta minus cosine theta. Again, theta goes from 0 to pi. Well, let's see. What is sine of pi? Sine of 180 degrees is 0. Sine of 0. So this term is 0. The electric field at the point P is 1 over 4 pi epsilon 0 lambda over r in the j hat direction, which is the vertical direction. It is pointing away from the electric field, the wire. Well, cosine of pi minus 1 with another minus 1, that makes plus 1, minus cosine of 0 is 1 with another minus, so it's minus minus 1. So this is 2. So the electric field is 1 over epsilon 0 lambda over 2 pi r in the j direction. Now, any questions in this derivation? Now, before you go, in fact, before calculating the integrals, we could have seen that the electric field had to be perpendicular. You see, here I imagined a segment over here. But for every such segment over here, there is a similar segment on the other side. And both of these segments, they will create electric fields of equal magnitude because they will be equidistant, but pointing in opposite directions. They will cancel the horizontal components, and we are left with the vertical component only. So before we start the computation, we could have seen that the electric field had to be vertical and then evaluate the vertical component only. But this is also, we showed it explicitly. Okay, see you on Thursday.